Okay, I'll make that a couple of minutes past the hour, so we'll make a start on today's webinar on the ABEM WalkTEM 2. So thank you very much for joining us here for another of the Guideline Geo webinar series. We've got quite a few more to come through the year, so hope you enjoy this. For those of you who don't know me, my name is Jimmy Adcock. I'm the manager for the ABEM product line at Guideline Geo. I've been doing this role since the end of summer last year. Before that, I spent 5 years as an applications engineer for Guideline, doing training and sales and technical support. Just in case there's anyone who's actually new to Guideline Geo entirely, we're an equipment manufacturer. We make geophysics equipment, and we have 2 brands. We manufacture ground penetrating radar systems under our Marla brand and more traditional geophysical equipment under the ABEM brand. So that is seismic, resistivity and TEM. We've got offices spread across the world, so we cover most of the time zones pretty well. And these offices are a mixture of sales staff, technical staff, but of course the heart of the company is in Sweden. So our head office is in Stockholm. We have our research and development in Umeå in northern Sweden, and then even further north, we have the factory where all of the equipment is made up in a town called Marlow. I'm based in Manchester in the UK, but really what we're here today to talk about is the WalkTEM 2. This is the latest offering in our TEM series of products, and we launched it at the beginning of last month. So hopefully you'll have seen some of the press surrounding that. And today we're going to look briefly at the TEM method, how it works, so that we can understand what we're trying to do with the system, and then we'll look at the product itself. The theory is kind of helps us to understand why we've included some of the features that are on the WalkTEM 2, where we're trying to make the system easier for people to use. So what is transient electromagnetics? Well, it's a method of mapping the subsurface, and with the WalkTEM, it gives us a 1D resistivity profile, a bit like VES, but operating on different principles. So why would you use it? Why would you use this different methodology? Well, it's entirely non-destructive. We don't have to have electrodes in the ground, and the field setup is very simple. We have a transmitter loop around the outside, and then 1 or more receiver loops, normally at the center of that transmitter. Then those are attached to the instrument, and the field setup maybe takes 20 minutes. It's suitable for kind of all stages of prospection. So we can search, we can map, and we can also monitor resources. So we might use the system with large spacings between our measurement centers. So just basically moving across a landscape to try and identify where a resource might be. And then we can come back and do a more focused survey with closer spacings to actually map its extents. And if suitable, if it's something like an aquifer, we can then repeat those measurements over time to see how the situation changes. For example, how an aquifer draws down during the summer months, how it recharges during the winter months, how increasing population might actually affect the level of that aquifer. TEM is actually very responsive to conductive bodies. That's what we're basing this on. It's trying to induce currents within these conductive materials. And it's very good at being able to differentiate between materials that are very conductive, much better than traditional electrical resistivity methods. So that pushes you towards a certain set of applications, and primarily it's groundwater, mineral search, and certain environmental applications where we might be mapping, for example, permafrost or meltwater in glaciers. Anything basically where we have something conductive as a target. And of course, the final thing is that it is very quick as a method. As I said, it takes maybe 20 minutes to lay out the loops, get connected up. And then the soundings, an individual sounding is going to take something between maybe 3 and 10 minutes, depending upon how many repetitions you want and the kind of depth that you're trying to achieve. So if you compare that to the time it might take to do a VES measurement in a water prospection survey, there are some real benefits to come from using TEM. We can cover much larger areas much more quickly. But what about the system itself? What about the WalkTEM 2? What's that going to bring to us? Well, I've been pretty broad here with my slide, and I've just picked sort of some key attributes. So precise, rapid, rugged, flexible, easy. I know they're all really easy words to pick and to put onto a slide, but after we've talked about the method and then how the instrument uses that to give us a result, I'm going to actually justify these terms, and hopefully then you'll agree that I haven't just opened the dictionary and picked some random words. So let's start with how TEM works. What does it do? Well, the basis is a very simple physics principle, and that is that if you run an electric current around a wire loop, you actually set up a magnetic field around that. So here in this image, we have our schematic of a transmitter loop in red with current flowing around it, and then the magnetic field lines shown in yellow that gets set up whilst that current is flowing. We then switch the current off really quickly, and by doing that, that magnetic field collapses. And that collapse of the magnetic field means that there's a lot of energy that has to go somewhere. We can't just lose energy. You know, it needs to be transferred. It still exists, and the way that that we remove that energy with that collapsing field is we induce electrical currents in the ground beneath the transmitter loop. So as that magnetic field collapses, we see these currents start to develop in the ground beneath, and they will then spread out and get deeper over time. And the way that they spread out and get deeper over time tells us something about the structure of the Earth. One way to think of this is to imagine an open pipe that's carrying a flow of water. And if there's nothing to obstruct that water and it can flow unobstructed around the pipe, then we're in a kind of situation of stasis. Everything is fine. But if I was to suddenly put something in the way of that water and stop the flow, then I would get this big splash. And effectively, that's what we're doing, just kind of an electronic version of it. So we're running that current round and stopping it really, really quickly. And the splash is effectively what we call an electromotoric force, an EMF. And the more force we have, the deeper we can see. So how can we control the size of that pulse? Well, if we use more current, that's like making the water flow quicker. So more current, bigger splash, we should be able to see deeper. Also, if we make that transmitter loop bigger, it's the same kind of thing as making our pipe bigger. We've got a greater weight of water behind any point in that system. So as soon as we stop it, we get a bigger effect. So more current, bigger loops, bigger splash, deeper measurement. So once we've set up those currents in the ground, they're going to do exactly what the transmitter loop did. They're going to actually create a magnetic field around them. And it's that that tells us about the structure. So our receiver loop at the center of the system can detect that magnetic field and look at how it decays over time, looks at how it gets smaller as those currents get deeper and deeper into the ground. So a measurement isn't just kind of a single injection of current and then switching it off and then seeing what happens. We actually repeat that process hundreds of times. And so a measurement cycle looks a little bit like this diagram at the bottom, where we put the current on in one direction, a positive direction, switch it off, and then once the current is off, then our receiver measures that magnetic field strength. Then we put the current on in the opposite direction, switch it off really quickly, and measure the effect again. And we keep repeating that process. And by cycling between a positive and a negative pulse, we can avoid generating any kind of drift. So we don't charge the ground up in one direction that would ultimately affect the measurement we're making. Theoretically, by the time we've finished the measurement cycle, the ground should be back in a similar state to we found it. Well, what do we get on the instrument? Well, you know, what is the end result from all of this? Well, effectively, the instrument is just measuring the strength of that magnetic field, and it's measuring how that changes over time. So we can then convert that value into an apparent resistivity. And that's what we've got in this graph here. We've got apparent resistivity on the y-axis, and we've got time along the bottom axis. So we're measuring how long after we switch the current off, how does that apparent resistivity change through that time. We call it apparent resistivity because, of course, any of the currents that are flowing at depth, what we measure at the surface has been affected by all of the layers in between. So we can't make a direct interpretation from that raw data, from that apparent resistivity. We need to take that, put it into an inversion software package that will then try and find a model of layers and resistivities that will give us the same data that we've brought back from the field. So this is what we've done here. This on the right-hand side is a model of layer thicknesses and resistivities that match the data recorded on the instrument. Now, the great thing about the WalkTEM is that you can do that processing step on the instrument itself. We don't need to take the data off, put it onto a laptop and do some processing, a couple of button presses, and we can actually have a result there and then in the field to give us a preliminary idea of the geology that we're operating over. Once we've done that processing step, then we can start to assign interpretations based on the resistivities of the different layers. We can either attribute particular geological materials based on the resistivity values, or we can say that the geological material has been affected, its resistivity value has been affected by some kind of material within it. So either the presence of water, which would reduce the resistivity, the presence of saline, which would reduce it even further, or mineral deposits that again are very conductive and would therefore reduce the overall resistivity that we see. As I say, we can do this processing on the instrument, but we also would normally pair it at a later date by doing some processing on our computer. And we would use Aarhus Sphere TEM to allow us to actually refine the model that we've created. When we do the processing on the instrument, it's using automated settings to decide which data to keep and which to reject. And it uses an automated starting model to create this final result. So we can be a bit more refined when we use the desktop version to make sure that we're getting the most reliable result possible. And we can go beyond 1D, just having a resistivity sounding, by actually plotting our data into their relative positions to each other and looking at how resistivity changes in 2 or 3 dimensions. So in this example here, each of these black dots is a TEM sounding, and this is within Aarhus Workbench, which then allows you to combine the data from all of those different measurements. And you can see at the bottom here that we've made a 2D profile with the ground surface at the top, and then the resistivity values shown by the color scale. And we have a paleo river channel that's cutting into some very conductive clays that are shown in blue. So we've got sands and gravels in the middle, clay underneath. We can then slice that horizontally so that we can see how the resistivity changes at different depths and generate maps of that. And we can even map the depth to a particular layer. So in this instance, you can see there's a black line that marks the contact between the sands, the gravels, the glacial till, and the clay that's underneath it. So we could plot a map of the depth to that layer. So those are our outputs, and it's, as I say, a very quick methodology. That data set there are actually a total of 16 soundings in this that were spread over a 1.5 kilometer distance. And those were collected by sort of a 2.5-man team in the space of a day very easily. I say 2.5 because 2 people were carrying the heavy equipment and the 3rd person was just driving the car from field to meet us. There's a couple of other little bits of theory that I'd like to touch on as well before we get on to the instrument, because we're going to talk about some of the functions that are on that machine. And to really understand the benefit that they bring to you, it's useful to understand what we're trying to do in the background when using those particular features. So One thing I want to talk about is waveform analysis. And what we're talking about there is the shape of the current pulse. So we switch the current on, we switch the current off. It's impossible to make the current just immediately hit its maximum value. Electronics define that we can kind of build it up to a particular level. And similarly, it's very difficult to switch a current off immediately. There's always some kind of tail where the current reduces. Now, the shape of that pulse going on and then coming off again is going to affect the transient, these currents that we are inducing into the ground. And so that can affect our interpretation, our model that we build in the inversion software. So if we can tell the inversion software exactly what that waveform looks like, we should get a more reliable model. And with WalkTEM 2, we've gone to a lot of trouble to really map in much more detail the way that the current switches on and off on the individual instruments. But actually what this slide is going to talk about is something slightly different, and that is damping. So this is talking about that very moment where we switch the current off at the end of the pulse. We have to have some kind of damping in the system, because what happens is we get a lot of noise. What we're trying to do is quite brutal in electronic terms. You know, we're taking a very high current and we're switching it off very, very quickly. And if we kind of consider our water example again, if you imagine after I've stopped the flow of water, that big splash, what's going to happen after that? Well, the water's going to kind of wash backwards and forwards. There's going to be a bunch of waves going around that pipe. And it's similar in our transmitter loop. After we switch that current off, we have that big pulse, and then we get a kind of resonant current that bounces backwards and forwards in the transmitter loop. Now we can reduce that by putting what we call a damping resistor onto the transmitter loop. And that damping resistor changes depending upon the size of the loop and the type of ground that we have the loop laid on. But how do we know? How do we know if we're using the right resistor? Well, that's the difficult bit. If you imagine the resistor to be a bit like a lid on our pipe of water, if I have the wrong resistor in place, one of two things is going to happen. It's either not going to damp the system enough, and so my waves are still going to be splashing backwards and forwards, or if I pick the wrong one, it could be kind of too good, and it damps the system to such an extent that I don't even get the initial pulse. So before, on the previous instrument, the only way for us to be able to determine which was the best resistor to use was to actually look at the raw data that we were collecting, look at our decay curve, and decide whether the resistor that we'd put in place was the right one or not. And that was something that was quite tricky even for experienced users. So for people who were starting out with TEM, this could be a bit of a problem, because you could end up with data that was either, in worst case, unusable, but in sort of less drastic cases, you could end up with data that is far noisier. So now we give the customers the opportunity to actually test the damping resistors using what we call a Rakovsky coil, which is a little bit of electronics. And this is a Rakovsky coil here that attaches to one of the inputs on our instrument. We pass the transmitter loop through the coil, and it can then analyze the switch off of the current. So on the instrument, we run a test measurement, and then it will show us the result of that. And so these curves are showing us how the switch off looks like for all of the different damping resistors that we have available. And you can see on this purple one that it kind of jumps up and down quite a lot. There's a lot of noise in that transmitted pulse. And that's exactly the same as these waves in the water trough. So what we're trying to find is the resistor that gives us the fastest turn off, the best pulse, but at the same time flattens out the quickest, so that we end up with a nice clean break at the start of that measurement. So we'll look again at that a little bit later when we look at the instrument. In terms of when that's available, it's included on the advanced instruments, and we offer it as an option on the standard units. And then the final bit of theory I want to talk about is dual moment measurements. So the moment in a EM system is the pulse. It's how big it is. So you can have a big moment that gives you the great depth, or you can have smaller moments that allow you to measure in more detail near surface. And why we might want to have a dual moment system measuring with both high and low current is all about having the kind of best of both worlds, being able to measure near surface and at depth in a single measurement cycle. So we said that if we want to go deep, we need to have either big loops or big current. Well, big current is great, but the issue that we come up against is that if there is any current in the transmitter loop, then we can't start our measurement, because if there's current in the transmitter loop, there'll be a magnetic field associated with that, and it will be much, much stronger than the field that we're trying to measure from the transient within the ground. So for that reason, we have to wait for all of the current to disappear. And if we have a large starting current, that time that it takes is going to be longer. And the longer that time is, the further that transient will have traveled into the ground, and the more information we lose near surface. If we reduce the current, then of course we can actually start to measure much, much faster, and we gain additional data in those early times. But the payoff is that smaller pulse means that the energy that we have will get absorbed quicker, and we don't get the deeper data. So on the WalkTEM, what we do is we alternate between high and low current repeatedly, and then use both data streams to generate one combined decay curve. And you'll see that actually, in reality, the difference between what I showed in the kind of one of the early slides and what happens in reality is that we alternate between these low and high moment measurements. So there's also the question of, is TEM the right method to use? You know, is this going to kind of answer the survey questions I have? Is it going to be appropriate for the application that I'm working on? Well, in that basis, you can pretty much determine it on just 4 questions. The first one is, what is it you're trying to do? What are you trying to map? The second one is, where are you trying to map it? The third one is, how deep are the targets that you need to detect? And finally, are you looking for big, broad features or very narrow, confined structures? So great answers, like the perfect answers to these questions are, our targets are conductive. So groundwater, saline intrusion, and mineral deposits, excellent targets. In terms of where we're going to be working, we would love to be working in big open spaces, so we've got plenty of space to lay the loops out, and away from infrastructure. So the problem with a TEM system is that we make this big pulse to induce currents in the ground, but we will also induce currents in other conductive things that are around us. So pipes, cables, buildings, you name it, if they're close enough, they will generate their own field, and we will start to detect that rather than what's coming back from the ground. So the rule of thumb is that you need to have the nearest piece of infrastructure twice your loop size away from you. So if you're using a 40 by 40 meter transmitter loop, you want to be at least 80 meters away. Depth, anything within 600 meters of the surface is a pretty easy target for the WalkTEM system and the power that's available with it. And then ideally, you're going to be doing sort of survey for larger deposits rather than very confined features. And that's not really to do with TEM, that's more to do with the fact that it's a 1D method. We end up with this resistivity sounding at a single point. And so if we're looking for something that is very confined, then obviously we would need to be quite close to it to detect it. So the converse of that is that, you know, the less ideal answers to these are very thin resistive layers. TEM doesn't respond well to those at all. You'd be better off using traditional electrical resistivity methods. Urban areas, built up areas where we've got lots of buildings, lots of utilities, they're not really going to be suitable for TEM. When you get beyond 1,000 meters, that's pretty difficult for the kind of size system that we manufacture. Guideline, we've always focused on near surface geophysics, and I think it's probably fair to say that beyond 1,000 meters, you're moving away from that near surface tag. And then, of course, as we say, these confined structures, you might be better off using a 2D method such as ERT to detect those, because you will have that greater density and that lateral spread of data to help you identify them. What does a system look like? What does a TEM system look like? Well, we kind of saw in one of the earlier slides, but this is kind of a bit more detailed. At the center of our system, we have our receiver coils, and you can see here that we have 2 different sizes of receiver coils that are then attached back to the receiver part of the instrumentation. And the reason why we might want to use different receiver loops or different receiver sizes is that the very small ones can respond very quickly because there's less wire within them. So that means that they're very good at mapping the responses that come from near surface. Immediately after we've switched the current off, the magnetic fields change very, very quickly, and they're moving very fast through the ground. So small responsive loop is excellent for capturing those. The larger loops scoop up more of that magnetic field, so they're much better at being able to respond to those later times where the signal strength is much, much smaller. So using the 2 in unison can actually, again, give us the best of both worlds. Around the outside, we have our transmitter loop, and that is then connected back to the transmitter part of the system. And again, we said that bigger loops allow us to create a bigger pulse and therefore look deeper into the ground. Now, this is obviously a difference. Anyone who knows the original WalkTEM, they'll see that, well, we originally used to have the receiver and the transmitter in a single box for this kind of the normal system, the regular system. With the WalkTEM 2, we decided that we wanted to increase the amount of power that we had in the transmitter, and we also wanted to offer more options to customers so that there was a wider range of systems for a wider range of applications and budgets. And to do both of those things, moving the transmitter outside of the receiver really helped us. So now we have a 20 amp transmitter, before we had 15, and having that increase in power of 1/3 just really meant that putting them both next to each other, transmitter and receiver in the same box, was going to be, potentially problematic. So shift it out, give us more options in terms of scaling the system, and everyone's a winner. If we now look at those individual components, starting at the center and working out, we have our receiver loops, and we said there's 2 different sizes, a small rigid one and a larger flexible loop. And those are tuned to the shallow near surface responses and the deeper, slower changing responses. If we then look at the transmitters themselves, we have a choice now of transmitter units. We have 2 which are actually upgradable. They are the same hardware in the box, but the specification is controlled by a license code, and that's the TX8 and the TX20. The smaller unit has a maximum of 8 amps, and unsurprisingly, the larger unit has a maximum of 20 amps. And so really the difference between them is that if you go for the smaller specification, then that will be for your shallower applications, whereas if you plump for the larger system, then you've got a much greater range of depths that you can go after. But as you say, you can start off with the 8 amp version, and if you decide that you need more power, you can upgrade remotely. So you pay for a new license code, and that can be installed almost immediately. So there's no requirement to send the system back to a guideline distributor to have that done. Then we have the kind of father of the situation, that's the TX60. This is the big transmitter, and this one goes up to 60 amps. So this is for people who have a real requirement for very deep measurements, and because it's focused on the deeper applications, it doesn't have the dual moment. It doesn't have a low current pulse and a high current pulse. It just purely puts out the maximum available to it with the batteries that are attached. So for the dual moment, use the TX8, TX20. For the really deep stuff, use the TX60. Of course, we have a very wide range of transmitter loops, various different sizes. Again, with the smaller ones suited to shallow exploration and the larger ones for the greater depth. And then we have the choice of receiver unit. So whether we go for a standard or an advanced. But like our TX8 and our TX20, that is upgradable remotely. So the specification, again, is controlled by this hardware license that we have. And so if you start with the standard, decide to upgrade, it's a very, very simple process. You just put the instrument online and we can upgrade it and you'll have access to the increased specifications. So looking at what the difference is between them, our advanced unit actually has both measurement channels available. That allows us to connect two antennas at once. So we can either have two of the rigid small antennas, one in a horizontal orientation to measure the vertical component of the magnetic field, and one sat vertically to measure a horizontal component, so that we can start to get an idea of the shape of that magnetic field, which is really useful for mineral exploration. Or we can use both the small loop and the larger flexible loop at the same time, so that we've got both shallow and deep information. Kind of related to that, the advanced is compatible with both of the receivers, small and large, whereas the standard only uses the smaller receiver. The advanced also is compatible with all of the transmitters and all of the transmitter loops. We said earlier that the advanced also allows us to do the waveform recording and analysis. So that's the testing of the damping resistors to make sure that we set the transmitter and its loop up perfectly every time, first time. And also the advanced is the one that has the onboard inversion. So it has this special version of SPIA-TEM pre-installed so that you can do your processing in the field. Regardless of which you go for though, with either of those, you'll get the dual moment, you'll get the high and low current pulses, provided you're using a TX8 or a TX20. You have internal damping resistors, so rather than having to attach them to the transmitter loop outside where you could forget to take them with you or lose them in the field, these are all built into the transmitter themselves, and we can use that to swap between them. And we also have a change in the battery technology. So with the WalkTEM 2, we've introduced lithium-ion batteries, and we have 2 units in there, just slide in and out, which means that you can actually hot swap during a survey so that the receiver unit doesn't ever actually have to be powered down. If we look at how these might look, how the configurations might look, these are probably the 4 most common combinations of receiver and transmitter. And effectively, as we move from left to right in this table, you're going to be adding more features and then deeper capabilities. So with the kind of entry-level model, where we have the standard receiver and just the smallest transmitter, the TX8, we can see that by jumping up a step, where we keep the same size transmitter, but move on to an advanced receiver, then we basically get the extra functionality of having onboard inversion and the waveform analysis. But we also can now use all of the transmitter loops and both of the receiver coils. So we would increase our depth actually without increasing the power that we're using, just by having a better recording of the signal that's coming back and the ability to use larger loops. From there, as we move to the right, then it's all about adding more power, adding more current to the transmitter and giving us that bigger pulse to start. So if we look at some of the configurations, this is our kind of entry-level model, which is the standard receiver TX8, smallest of the transmitter loops, which is currently a 20 by 20, and just the RC5 at the center. So you can see this is shallow applications, but not only that, this can be useful for customers who, if you're interested in some kind of proof of concept, making sure that the system is going to work for your needs, well, then you can come in, a relatively affordable budget here. Or if you need to spread your investment over time, you can start with a small system like this. And because of the remote upgrades, it's very simple to get into a system that then is much bigger and much more capable at a later date. So speaking of which, this is probably going to be one of the more common configurations, and that is the advanced receiver. So it's got the extra functions. It can work with all of the transmitters, all of the loops, and but with a 40 by 40 transmitter loop. And that's a really good kind of mid-ground transmitter loop. It's easy to use in the field. It's not too big. You don't need a huge amount of space to lay it out, but it gives you a really usable range of depths, as shown here. So a real good kind of catch-all setup. And then, of course, we could go up to the very largest configuration, which would be to have a 200 by 200 meter transmitter loop encompassing 4 hectares of land. Our larger receiver loop at the center, because, well, there's no point having an antenna that's focused purely on the shallow responses when you've got such a big loop, and the TX60, which is putting a lot of current in there, because by the time we've switched that current off and the current has gone from that large loop, we won't see a great deal of detail near surface. So this is for people who really have to hit those great depths and don't necessarily need that detail near surface. But because it's all modular, you can have in the back of the van a smaller transmitter, smaller loops, and you can basically plug and play whichever you need for that particular day's survey. I said that I'd come back to these terms, so I thought I'd just look at these before we actually go on to the user interface of the software to finish off. So what does the WalkTEM 2 offer? Well, precision is coming from a really broad dynamic range. We have the ability to record very small signals in great detail, but also very large signals without having to clip the responses that we're getting. We have calibrations built into the instrument that are setup specific. So as you go through the user interface, setting up transmitter loops, receiver coils, and different currents as you put more power into the transmitter, the system will automatically be picking the best calibration for that particular combination of hardware. We've got the waveform recording to make sure that we always have the best damping resistor, so the transmitter is set up for the best possible way it can. But also then when we take that data out and put it into the inversion software, we're giving it a true representation of what that transmitted pulse looks like, so it can give us a more reliable model at the end. We've talked about the fact we've separated out transmitters and receivers, again, to just reduce the risk of noise, having this more powerful 20 amp transmitter. And we've moved across to a plastic housing for the same thing. We were redesigning the system. We decided to actually do away with the metal casing and have an even lower noise housing on the system. We talked about how fast it is. We've got not just the layout in the field, which is quick, but we have the dual moment, so you don't need to repeat measurements, one set up for shallow, one set up for deep. We just let the instrument run, and it will collect both into a single data file. So when we come to do the post-processing, we're not having to combine data together. It's all in there in one curve. We've got the dual input so that we can measure either more than one component at a time or use different sized receiver loops at the same time. We've maintained the IP66 rating that we've got on all of our ABEM equipment. So that is protected against high pressure water and dust, and that's even during the measurement. So you don't need to worry about where you're working, and there's no external PC to worry about dropping or getting weathered. With the WalkTEM 2, we've tried to make the system more flexible as well by having more receiver options, more transmitter options, so that you can really find a fit for your particular application, your requirement, or even your budget. We've got this bigger range to hopefully assist you in finding the perfect instrument fit. And we've tried to stick with a really straightforward user interface that has a kind of flow from the point where you've set the instrument up and switched it on, going through, selecting your hardware, and then undertaking the measurement and doing the onboard processing. And so on that topic, let's actually have a look at the instrument just to finish off. So I've got a WalkTEM 2 on my desk next to me, and I've actually connected to it via TeamViewer. So this is actually a live picture of the screen. So if I actually press the buttons on the front of the instrument, you can see that I'm selecting different items on the screen there. And when we boot the instrument up, this is the screen that it comes into, ready for you to define how you want to set your measurement up. I can use just the buttons on the front of the instrument to do all of the control. There's no need to have an external keyboard or an external mouse attached whilst you're doing field measurements. So you can see across the top there are actually 4 tabs, and if I just press the page down button on the front of the instrument, I can switch between those. And if I actually start on the far end, you can see that we have our administration page. And so this is telling us what hardware license we've got on the instrument. It allows us to decide whether or not we want to keep the same measurements from project to project, or whether every time we create a new project that we start from scratch with the setup. And it also allows us to define the power line frequency. So we have scripts, measurement scripts preloaded onto the instrument, and those measurement scripts are written in such a way that the electromagnetic noise that is around us all the time from the national electricity grid is removed just by virtue of how we're recording the data. So if you select in here the transmission frequency for your country, and I'm in the UK, so it's 50 Hertz, then the system will only show you the scripts that are suitable for your region. So if I go back to my configuration page, so I've started the instrument up. First thing I would do on my site, say, right, fresh site, fresh project. Then I can select the measurement script I want to use. And we have scripts in here that have different measurement lengths, i.e. allow you to measure for longer and therefore deeper. Different duty cycles. So how long is the transmitter on compared to how long is the transmitter off for? We also have dual moment scripts, so that's alternating between low and high current, and also ones which only have a high moment pulse for when we're doing those really deep surveys with the bigger loops. In the support documentation, we have a big table that tells you exactly what each of these scripts are best suited to, so it's hopefully quite easy to choose the best one for where you're working. It always gives us a summary beneath of what that script looks like. So how long is the current switched on for? How long is the current switched off for? And how many repetitions are there within that script? How many individual readings are we taking within there? And you can see that there's hundreds of repetitions in there, which means that we're doing a really big stack to improve the signal to noise ratio. We can actually then increase that stacking even further by repeating the measurement script. So we just tell the instrument how many times we want it to run, and it'll then give us an estimate of how long that measurement is going to take. So we can see at the moment it's going to take 72 seconds to run this. We find that if you go above 3 or 5 repetitions, you don't really see a huge improvement in the data quality. So even then, you're not talking about a particularly long period to get a decent sounding. We then tell the system which transmitter loop we have attached to the transmitter. We can choose a damping resistor, either an external one or one from the internal array. And if we don't know which one to pick, then we can just hit the analyze button and it will go through all of them for us, and we can then see which one performs the best. We then drop down and tell it which receiver coils are attached to the 2 inputs on the end panel of the instrument, and whether we're measuring a Z component, an X component, or Y. So whether we have the antenna horizontal, vertical in that plane, or vertical in that plane. You can also put in an offset in there. So normally we have the receivers at the center of the transmitter loop, But if we want to do an offset configuration, then we just need to measure the distance from the center of our transmitter loop out to the center of our receiver loop. And these are kind of the coordinate directions for determining whether it's X, Y, positive or negative that you need to put into the boxes here. If we've got a monitoring project, then we can also ask the instrument to do repetitions. So in here, we just define how long we want the instrument to wait after the initial measurement has finished before it then starts the next one. And it will just keep then repeating those measurements, and each measurement comes in as a new station, a new data file within this project area. So that's it, that's set up. I can now page down onto the data collection screen, and I can just press start. And so we can see here that it gives us a summary of how we've set the instrument up. Unsurprisingly, I don't have a GPS location because my WalkTEM is sat on a desk in an office. Then we've got information about our transmitter unit at the bottom, basically the voltage that is on it, so how many batteries do we have attached, and how that voltage changes during the measurement cycle. So is our battery suffering when we're trying to inject current? Then on the right-hand side, we actually have the kind of live visuals of the data. Now the data, these decay curves are going to look terrible because I'm measuring on a desk, but we can look at the input channel and A or B. So we've got an RC5 attached to one, the small loop, and the slightly larger receiver loop attached to the other. And these first two will just update every time a new data stream comes in. So every time there's a low moment measurement, it'll plot that. Every time there's a high moment measurement, it'll plot that. And every time there's a noise measurement, it will plot that. So a noise measurement is where we don't put any current in the loop, we just measure the electromagnetic fields that are always around us. If we want to look at one in particular, then we can use the later tabs. And again, we can jump between those using the keys on the front of the instrument. And so we can see channel A high moment, channel A low moment, channel A noise. When the measurement finishes, we get a visual on the screen and also an audio signal, which you may not be able to hear, but every system comes with a Bluetooth speaker that you can pop in your pocket. So that if you are doing a longer measurement and you're trying to do a bit of multitasking and get on with something else whilst the instrument is collecting data, you're not sat there after it's finished, just waiting for it to complete. We then jump onto the post-processing screen. This shows us all of the projects we currently have on the instrument. And if I expand one of those, we can see the measurements that have been taken. So this is the one that I've just made. And we get kind of a bit of header information about it and how it was set up, how that data was collected. Now, I'm not going to try and do anything with that data because obviously it's from a desk. So I'm going to grab a data set that was collected outside. So if I right click, I have a bunch of options here, which are also then repeated in this shortcut menu on the right-hand side. So simple key presses to look at there. So I have a choice in here of sort of normal, typical file management that you would expect to see, but I can also model the data, that's run the inversion, which is of course included on the advanced models, but is not on the basics. So if I've got a standard system, then I need a way to look at data. So we also have an option here just to plot it. So at the end of the day, we can review our measurements and make sure that what we're taking back to the office is a good data set. So our little viewer, this is from a measurement with just a single receiver at the center of the transmitter loop, an RC5. This shows us in blue the low moment measurement, the small pulse, in red, the higher pulse, and it's automatically detected which type of antenna was being used. And I can switch those off using the shortcut button, so I can just toggle whether or not I'm looking at the high moment or the low moment. I can, at the moment, I'm looking at the decay curve, and I'm looking at the stacked decay, but I can also look at the raw data where it shows me each of the repetitions that I made. And it'll also then give me an indication of where the noise floor sits, so the kind of average noise level. So we can see that we will probably have good data up until the point where we start to get into the noise, and that's where those individual measurements start to diverge. So as I say, that's looking at the decay curve. We can also look at apparent resistivity if we want, and again, looking at how that changes between the different antennas. We can zoom in and move around, so we can really look in close at our data and simply rescale with a single button, and also take a screenshot from there. Close that down. Of course, the other option on the advanced instrument is to actually invert the data, do the processing on the instrument. So as I say, that opens up a version of SPEAR-TEM, and we can just simply hit run inversion, because this version of the software is doing automated filtering for us. It's looking at the quality of the data points and removing the ones that it doesn't think are going to be useful to us. And then it has a predefined starting model that it will use to go through the inversion process. So again, in here, we've got kind of header information about how the data were collected. We can also look at the data in here, just in a similar fashion, look at the different streams of data. So high moment, low moment, small receiver, large receiver. And then once it's done the final step of the inversion, we should be able to see our smooth model. So we can see how resistivity varies with depth. We have our apparent resistivity against time on here, and basically a show of how well this model fits. And then we also have our estimated depth of investigation. So that green line is telling us that on this particular site and with this setup, the data is trustworthy to a depth of approximately 175 meters. And then after that, it's been impacted by the surrounding noise. So that gives us that initial impression, that initial overview of the geology that we're sat on top of. As you said, once you've done the processing, we can do normal file management stuff like export projects, delete projects. We can mark particular stations if we think they're good to take forward for further processing. So when we get back to the office, we know that the ones with the production mark are the ones that we should focus our attention on. So the instrument has a pretty simple flow between these three tabs. And quite often in a project, you'll be using the same setup from station to station. So literally all we're doing is sitting on this measurement screen, pressing start, allowing it to run, and then jumping to the post-processing to have a review of the data, and if we've got an advanced unit, to run an inversion.